Hi everybody, and welcome to your first video of Unit 1 on electromagnetic radiation. I want to get started by answering the question, why does the chemist care? Why is this even a topic on the unit that's supposed to be about the atom? The answer is that all matter, for those of us who study matter, which of course is made of atoms, the things we are talking about, all matter has the ability to emit or absorb this radiation. So as it turns out, understanding the radiation itself is just a really good way for chemists to probe the structure of the atoms themselves. So try to keep that in mind as we move forward. Let's get into some specific details on electromagnetic radiation and define exactly what it is. Technically, electromagnetic radiation is simply a form of radiation that can be described in terms of two things: an oscillating electrical and magnetic field. That sounds really confusing. It's hard to imagine. The gist of that statement and what really matters is that this radiation travels in the form of waves. These waves are not your standard sound waves, like sound needs air to travel through, or ocean waves that need water to travel through, but they are waves nonetheless. And as waves, there's two terms you have to be familiar with for us to kind of go forward. Those terms are wavelength and frequency. Now, even though water waves are not the same kind of wave, we're still going to use water waves as an example to understand these words. First of all, wavelength. We'll start there because it's kind of the easier of the two. Wavelength is, it's just that. It's the length of the wave. Imagine measuring from one crest over here to the other crest. That would be the length of the wave, or the wavelength. Frequency is a little bit tougher. For frequency, let's draw some lines in here. If you imagine designating any random point, any random line in space, we'll pick right here. And then imagine as this wave moves past that point. So if the waves are kind of sliding in this direction, if you counted how many waves passed this point in a given time, that would be the frequency of the wave. So if one wave passed through here in 1 second, that would be the frequency of that wave. But if a different wave passed through 3 times in a second, that would be a different frequency. So now that we understand these terms a little bit better, let's move forward and look at the spectrum itself. You've probably all seen a diagram like this before, but I'm going to break it down and show you some of the important pieces. Up at the top, highlighted in red, first of all, these are just some of the common names we give to regions on the spectrum. Radio waves, the reason your car can play music when you turn the radio on. Microwaves heat up your food. Visible light that we can see. Ultraviolet, this is why you have to wear sunscreen. X-rays, used of course to image the inside of your body. All of these should sound pretty familiar to you. Moving down the chart, highlighted in yellow, we have wavelength come into play. You can see very long waves up here, very short waves down here. Just to give you some perspective, the longest waves, radio waves, are so big, 10 to the 3rd meters, they can be about the sizes of buildings. The waves that make up visible light are so small, 10 to the -6th meters, they're only about the sizes of cells. And X-rays and gamma rays are even smaller, so small they're about the sizes of atoms, or even the nuclei within the atoms themselves. Moving down, we have frequency highlighted in green. You can see these numbers here are measured in hertz. That's how many waves pass that given point in space per second. The word we use down here is these are very low frequency waves. That means very few waves pass a given point in 1 second. That's the time. Up here at the what we call high frequencies, that means many waves pass a given point in that same 1 second. You can make a connection to the wavelength. It should make sense that very long waves are going to have lower frequencies because less of the waves will pass that point in that given second. Whereas if the waves are very short, then it makes sense that a whole lot of them would pass that same point in the same 1 second time. We can also connect this to energy, and this is an important one for chemistry. The very high frequency waves are said to have a very high energy value, whereas the lower frequency waves are said to have a lower energy value. And lastly, down at the bottom, just to pull out the very small piece of this that we can observe with our eyes, the visible light portion, you should know that purple and blue light is the shortest wavelength, highest energy type of visible light, whereas red light down here are longer wavelengths and the lowest energy type of light. So that pretty much sums it up. Now there's a lot of information on this chart, and in AP Chemistry you do not have to memorize it all. That'd be crazy. However, there are some summary statements from this that you would be expected to make. Number 1, you should know that longer wavelengths always correspond to less energy. That's down here on this end. You should also realize that high frequency waves always correspond to higher energy waves. That's up here on this end. We'll also focus a lot on the visible portion of the spectrum in chemistry. So you should know that violet light is the highest energy, shortest wavelength type of visible light over here on this end, where as red, of course, is the lowest energy, longest wavelength type of visible light. That wraps it up for this video. Please enjoy the recap to follow.